this right here, I love this picture. This is a piece of paper that Isaac Newton drew on himself. This is his actual handwriting here using a pen, right? And so what he's talking about is inertia and gravity and the path something will take through space. Okay? So this is kind of an important thing. We got inertia and gravity working together in this picture here. And so let's go back to the camera and or to the paper, and I'm going to have you draw this. I'm going to explain what this is a picture of, okay? All right, so here's what it is. Now let's suppose you have the surface of the earth, right? And pretend you're standing on the earth for a second, and let's say you're throwing a baseball, okay? You're getting ready to throw that baseball. Now, if you don't throw it at all, if you don't apply any force to it, it will just fall down to the ground, right? And that would be gravity, is the tendency of it to go down toward the ground, which is really going toward the center of the earth. But that's gravity. So gravity, make it go downward. Now, if you had no gravity because an object in motion stays in motion unless acted upon by a force, well, gravity is a force. But if there was no gravity, the object would just keep on moving, whatever direction it's going, and it would just keep on going in a straight line. Okay? Now, but there is gravity. So let's say a 6-year-old girl throws the ball, and it's like, the gravity, or the inertia, is its tendency to keep going on its own after it's been released, after the force has been applied. Inertia. Okay? Going this way, and then gravity heading that way. So what's going to happen is as it goes that way, it's going to fall to the ground until it hits the ground. Okay? So you have inertia that way and gravity this way. I'll just put G for gravity. Now, what if somebody with a better arm than a 6-year-old girl threw it? Well, it'll have more force. It'll still take, by the way, the same amount of time to hit the ground, but it will go further in that amount of time, and then it hits the ground. And then suppose somebody with a really good arm, like a high school pitcher, throws it. It'll go this far. Well, suppose what would happen now if you had, I don't know, a pitcher from the professional baseball leagues, it would go a lot further before it hits the ground. Now, here's the genius of Isaac Newton. And he's thinking, okay, well, this is how apples fall and things. You got inertia and gravity. What would happen if... And so, let me slide this down a little bit. Okay, so you're going to need most of this page. It's a pretty big area here. So, let's say here's the planet Earth, in which they knew that planet Earth was a circle. Yeah, it was not a bad circle. A little bit bulgy on one side, but pretty good here. All right, so let's say, okay. I'm going to change it just a little bit, and I'll show you the actual analogy that Newton used, but I'll change it to make more sense for us. Suppose it wasn't a 6-year-old girl or somebody throwing it. Suppose it was Superman, and Superman is hovering out in outer space, right? And so here's a giant Superman ready to throw the baseball. There's Superman. There's his cape. All right. Now, if he throws it, he's in the same situation where he's in the gravitational field of the Earth, which, by the way, if you're in outer space, there still is gravity. You're just in what's called free fall, right? You're falling along with everything around you so you don't fall relative to your spaceship. Okay, so anyway, here's what happens. And Superman, if there was no Earth there, it would just keep going in a straight line, because an object in motion stays in motion unless acted upon by a force. That, again, is the inertia. All right? Now, also, you do have gravity, though. Its tendency to fall to the earth. If you just let it go, it would just plummet to the earth through the atmosphere, probably burn up, but whatever. And then you have gravity. All right? But what's going to happen is just like what happens with the 6-year-old girl. Here, let's actually keep this one in view a little bit. It's going to fall toward the earth. So Superman, though, has a really good arm. So when he throws it, it falls toward the earth, following the same kind of trajectory. But look what happens. He went around the curvature of the earth. So it's still the same distance from the earth that it was to begin with, right? The inertia is having its tendency to just keep going in a straight line, which without gravity, it would just go flying off into space. Without the inertia, it would just plummet to earth. But if you have the two of them balanced, it goes like this, and it's going around the curvature of the earth and till it's halfway around, and it's still the same height. the same altitude it was before, because its tendency, the inertia, is equal to the gravity. Its tendency to fly off into space is exactly equal to its tendency to fall toward the Earth. So what happens is, boom, it hits Superman in the back of the head. Oh, well, let's say Superman's smart enough that he goes, get it, and he dodges, it gets out of the way. What would happen is it would keep on going on the same path it was. And it would go around a second time and a third time. And if the two forces, well, inertia isn't totally, I spelled inertia wrong. If inertia isn't technically a force, it's a law of nature. But if the inertia and gravity are equal, then it will just go around forever and ever. And that's what Isaac Newton said is, what if you had a situation like this, but instead of a baseball, or in his case, he used the idea of a cannonball, what if it was the moon? And if the tendency to fly off into space, it's inertia, it's moving, nothing's pushing it because it's already moving. An object in motion stays in motion unless acted upon by a force. So what if the inertia exactly equals the gravitational pull pulling the Earth and the moon together? It would be in orbit, right? And you wouldn't feel the motion because you're not having, accelerating or decelerating. You're just an object in motion stays in motion, just like you don't feel the inertia of if you're sitting in a car, right? You don't feel like you're going 60 miles an hour. You might feel a little rumble from the tires. So that is what Isaac Newton came up with. He explained how it works, how orbits work. Let's go back to the screen here. Okay, so here's a picture that Isaac Newton himself drew, right? That's just like what we were doing. Now, this one isn't his handwriting, but it's in the book that was published. It was a more professionally done picture of it. But instead of it being Superman, Isaac Newton, his idea was, what if you had a really, really high mountain, the highest mountain in the world? And instead of Superman throwing it, it was a cannon. And you see, it would go this far with that much force, this far with that much force. And if you had enough force, it would just go around and around and around. So this idea of Superman that I said is exactly what Isaac Newton came up with. Orbits are a matter of balance between two different factors: inertia, which is the tendency of something just to keep on moving, and gravitational force. Okay, so orbits, inertia, and gravity, please write that down. And so again, the planet's velocity, it's its tendency to just keep going in a straight line. But as long as you have the gravitational pull of the sun, and that in the path around it, the orbit around it, would be caused by those two things being balanced. So the Earth going around the sun is also gravitational pull from the sun, right? Now, this is an example of inertia. If you're riding on a bicycle and your wheel gets caught in the grill of a drain or something, and your bike stops instantly, you keep going. Whoa! Right? That's inertia. That's a force or a tendency that Isaac Newton discovered and identified, and match that with gravity, you can have orbits. All right, I'm going to declare this lesson pretty much getting wrapped up, and I'll just leave you with this cartoon where it's like, nothing yet. How about you, Newton? Okay.